So, thank you all for coming. Today, I'll be the presenter. I'm presenting consumer journeys with nested Weitzman scores and informational complementarities. And this is joint with Simon and Maxim, who are also here. So, just as a you know, quick overview of what we're going to do, we're going to start with two motivating examples. I'm going to give a brief preview of the results. I'm going to then outline the model, discuss very key results, and then conclude. And this should take about 50 minutes if everything goes right. So to preview, I want to think about searching for a car to buy. So especially in the US, you've got dealerships. They tend to be closely clustered. So I want you thinking about 5 dealers. 3 of them are going to be north of town. 2 are going to be south of town. And then each of these dealers are going to sell 2 brands, and all brands are going to differ. And what we want to think about is the consumer search process and eventual selections in this type of world. So to outline this, we're going to use a tree. Trees are going to be common throughout this entire talk. And the idea is you can think about a root node attached to the 2 locations that a consumer can choose first, north or south. They can then go to dealerships. So after going north, they can go to D1. After going to D1, they can see brand 1 and 2 and select among them. And then after searching brand 1, they can see the cars. Now, the key, though, is we want to allow for a pretty rich consumer journey. So we want the consumer to be able to go back south after they go north, to be able to go to dealer 2 after they go to dealer 1. And we want to be able to have quite a bit of flexibility in this model while still having a tractable enough model to characterize these journeys and the eventual selections. So this is what I want you thinking about. Blue in this picture is the part that we fully drawed or fully illustrated. The orange parts, though, are the parts where there's more stuff that I just didn't draw. So if you go south of town, there's 2 dealers. At each of those dealers are brands and cars. Now for these 2 examples, for this one example, we're going to think about 2 versions of a price change. And the first one's going to be an advertised price change. So D1, dealer 1, adjusts the prices on all their cars downward and displays this to the consumer. So the consumer knows this prior to starting their search process. And we want to know how the demand for cars at dealer 2 adjusts. So there's 2 effects that's going to happen in a search model. The first one is that searching north of town is now going to be a better value proposition. So the consumer is more likely to aim north first or at all. Now that's going to be good for dealer 2, all else equal, because there's now going to be foot traffic coming north of town. However, the value of searching dealer 1, the value of searching brand 1 and 2 at dealer 1, and the value of selecting a car at dealer 1 also increase. And that's going to lead to a local competition effect. Once that consumer's north of town, they now get to pick among cars at dealer 1, 2, and 3, and that means that as dealer 1's cars get better, the demand for cars at dealer 2 goes down. Now, cars at dealer 1 and 2 could actually be gross complements if drafting effects dominate, even though only 1 car is being purchased at the end of this process. So depending on the magnitude of these effects depends on whether closely located products are complements or substitutes. Now, that is for an advertised price. If a price is hidden, though, you get very different results. Specifically, if the price is hidden on the part associated with one of the products and not the other. So in this case, D1 is going to decrease the price of car 1, though it could decrease the price of any of their cars or all their cars, but it's not observed by the consumer until after searching dealer 1. So the consumer does not know this when they're deciding whether they want to search north of town. So there is only going to be a local competition effect. This can only harm dealer 2. And that is because there's no adjustment in the anticipation of the consumer until after paying the shared search costs at north of town associated to these 2 dealers. So these are the kind of thought processes we want. 1, the locations in the search model are going to be important and the proximity is going to be important. And 2, the timing of when price is discovered is going to affect whether products are always gross substitutes or maybe gross complements. Now, the other example I want to use that I won't go that far into is just searching online. Searching online is an inherently good, I think, application of this type of model. And we represent it fairly simply on this as outside option or Google. Going to Google reveals Walmart, Amazon, and eBay. Then you can select options. But this model can handle basically any tree structure. And so you can have within platform search, across platform search. Amazon could have control over how the downstream, how the tree defined as a subtree of Amazon gets realized for the consumer. There's a lot of richness here that the model can admit. But the key features of this search process is to get to an option, there's going to be a few things that happen. First, information gathering can be costly, and that's true in just about every search model. Whenever we consider search, we're really thinking about information gathering being non-trivial. The other part of it, though, is that gathering information is rarely a one and done deal. In the real world, it's not just I search and I know everything about this product. Maybe there's an iterative process where I continue my search looking at the same product, or maybe there's multiple steps that I have to do to get to a product, right? We use consumer search to model what happens when somebody puts in a search at Google, but they also had to make the choice to start their search process. These multiple stages are going to be important. The other thing is that options that are similar often share search costs. So BMWs tend to be at BMW dealerships. Laptops tend to be in the category laptop. These correlated values are also going to correspond a lot of times to close locations in a product space. And then the next part of this is that acquired information may be relevant for related choices. So we're going to allow for some forms of learning here. There's going to be some limitations on what types of learning we can include, but there will be learning. So when you go to Amazon, you can learn correlated values about products at Amazon, positively or negatively. And then the last part that we definitely won't get to today is that our model doesn't really need the consumer to know the tree. They just have to have a distributional understanding of the possible subtrees they can face. So we can allow for a lot more ambiguity in this search process. So does anyone have any questions about the motivation before I go on to the overview of the results?
So the motivation is to do better demand estimation, or what's the question you're trying to answer here? I haven't got a clean sense of yet.
So yeah, it's to better represent the search process to figure out the properties of demand. I mean, the ultimate goal would be to do an equilibrium analysis.
Okay,
but for example,
but like for an empirical guy, I can think of this as helping me to do better demand estimation.
Absolutely.
Okay.
Right. So basically, we're gonna make search more rich, but along the way, we're gonna admit complementarities. So this is breaking you outside of what you could do with something like BLP, where you're stuck in the gross substitutes world. So the key here then is actually going to be this tension, which is we want to solve and characterize a model of consumer behavior that reflects key characteristics of consumer search, but we also want to be able to use an ordered search framework with Weitzman scores. We want to preserve the relevance of myopic scoring, or at least a version of myopic scoring. So our goal is to add richness to this structure, but not break scoring rules. And to actually just give a crisp example of something that would be ideal to do, but we cannot do in this current model, is that if when you go to Amazon, you learn about stuff at Walmart, you would update your score for Walmart. So when we're thinking about this, you can have downstream learning, but not cross learning. You can't learn about something at other nests inside of this framework. There are probably ways of adjusting it, but it's not going to be what we consider today. So there is going to be some form of learning, but it's going to be just the right form of learning to preserve Weitzman scores.
We're going to use. Can I ask you? So, how related is this to the literature on shopping malls? Something like, you have stores in the same mall.
Highly related if you use a specific version of this. So actually in the paper, we use what to me I think of as a mall model. So a lot of these features can come out of simpler models. So if your goal was just to show that these things can occur, right, so that you could have gross complementarities, you could think about just putting all of the products inside of one box, and then think about the consumer deciding whether they want to first open that box, and then once they open that box, they see all the items in it. And you can get a lot of the intuition there. And actually, that's what we do first in our paper. Before going into the kind of larger model, you can start in a simpler setting and get similar results.
And another question would be, so from what I understand, just before I start speaking, you said that you could allow that once I'm on one of the branches, that within that branch, somehow there's learning about other sub branches, in a sense that, so for example, me and Heskey, we have this thing on showrooming where the same products are carried by different stores. So let's say brand 1 and brand 2 in your example are at different dealerships. So it's basically perfectly correlated brands.
So I suspect that there is a way of implementing this if you set up the model right. But it's more that when you go to Google, you can learn something about Amazon, Walmart, and eBay. What you learn about Amazon, Walmart, and eBay could be correlated. You could learn good things about Amazon, bad things about Walmart, and good things about eBay. There can be a lot of richness. But once you go to Amazon, you cannot learn about Walmart in our model. Now, it's worth saying that that is to preserve Weitzman scores. But I think if you allowed for example, having a certain version of showrooming, I think you could allow for basically the first pathway to reveal extra information. So essentially, Weitzman scores would get broken once and things would still stay tractable, but we don't do that here. So showrooming is actually something that's like one of the simple things outside of the scope of what we can do. 1 second. Sorry about that. Dogs. Okay. So yeah, thank you for that question. And showrooming is actually something that I think would be worth adding, but will not be considered today. So the key though is that we want to preserve Weitzman scores. And so if when you went to Amazon, you learned about Walmart, you would adjust your score. And so it wouldn't be myopic. Now, the other part of this is the reason we want to do it is we want to take a tree and use eventual action arguments in it. So we want to take that min reformulation that's become popular in ordered search, and we want to make it a tree property. So we want to take this and we want to be able to deal with it in a much more rich structure. And we're going to see that very similar properties are going to hold. And the key idea of this is that you can do demands, you can do search volumes, but you can also do the demands for all products at a platform, for example, pretty easily with this model. And our goal is to illustrate how and why products may be gross complements in search markets. So while this is a cool exercise in theory, it will also very much expand us outside of the set of demand systems that you could get out of like a discrete choice model or a regular ordered search model. And then the key is that we're going to explore the role of price discovery, but not in an equilibrium sense in this presentation, more just when is a price discovered and how does that affect the structure of demand? Now, for policy implications, the goal here is to point out a key tension, once again, that regulators often oppose mergers between products that are firms that produce or sell close substitutes. So similar products tend to be something that worry regulators when they're looking to merge. The key, though, is that if you also have informationally close products, so if similar products are informationally close, you have to consider drafting effects and whether they might dominate in some settings. So we could theoretically be blocking mergers that are good for consumers. And the key to this is the fact that we study how demand is structured, and we're able to look at both product closeness in terms of correlated value and product closeness in an information sense, shared search costs. So I'm going to put up a literature slide. I think this has become common in these, where I'm just going to say there's a literature and I'm going to keep moving. But what I mean by discrete choice models when I say it here is models that don't have search costs. So you just have values and you select your highest value. Think when I say nested DCMs, I'm thinking nested logit or some sort of adaptation on it. Ordered search models are the ones that we've been considering here throughout many of the presentations. And I want to actually point out in 2 weeks, there's going to be another paper that does work towards extending Weitzman scores. And while it's not what we consider here, you could make it kind of a special case of this tree model, though we consider very different things. So I highly recommend seeing that presentation in 2 weeks. So I'm going to go right into trees then. And the idea here is, my hope is that most people are familiar with trees, even if it's just from game trees. But the idea is we're going to have a tree. We're going to use capital lambda to denote the set of nodes that are part of that tree. Lambda 0 is the root. Terminal nodes throughout these slides are going to be denoted with numbers, and terminal nodes are I in capital I. So these are things that you can select, and they have a value VI. We're going to be clear about how that value is structured and how you learn about it in a few slides. Then there are search costs. Search costs are associated with intermediate nodes. And each time you access an intermediate node, that's searching it. Anytime you access a terminal node, that's selecting it. We're going to use lowercase c for immediate children, uppercase C for all downstream children, for all nodes downstream. So C of A is B and C. Capital C of A is B, C, and 1 through 6, so on and so forth. This is just to establish some notation. You can then think about parents. So P of lambda is the immediate parent of lambda. That is the node just one up. Capital P of lambda is the pathway back from lambda to the root. And to simplify our notation, we include lambda in that set. So it's the shortest path from lambda back to the root, including lambda. And this is just some notation to start us off. And now we're going to get into a slide that I'm going to parse for you. And it's this idea that we're going to want to do a somewhat rich version of search, but we don't want to go anywhere near as far as what we do in the paper, which is more advanced. So we're going to think about this as values are going to be negative pi plus components of the value. And these components are learned on the pathway to this option. So as you go towards I, you're going to learn epsilon I lambda. So when you search lambda, that's what you're going to learn about I. And this is going to be heterogeneity. It's going to be independent of any epsilon j gamma for lambda not equal to gamma. So when you search lambda, you can learn correlated components of downstream values, but you're not going to learn correlations at different nodes. This is just to simplify things. Actually, a lot of this can be advanced further. It's just to clearly state what's gained in information and when. Each search cost is going to be IID, but once again, this can be relaxed to allow for correlation and different structures. But the idea is each search cost is IID here. The consumer knows the distribution of heterogeneity prior to search and observes the exact values of the epsilon and the search cost when searching the appropriate node. So search costs are discovered at the parent node. The epsilons are discovered at the current node for all downstream options. And of course, you can shut down parts of this by just setting these epsilons to 0. So for example, you could think about a model where you're just updating search costs until the end. The agent can initially access nodes that are immediate children of the root. So when the agent starts, they can access anything that's attached to the root. At each point in the process, so the agent has searched some set, lambda prime, the agent can access anything that's an immediate child of that set, but isn't in the set. In theory, though, they could re-access something in the set. They would just pay a search cost and gain nothing. If the agent selects a terminal node as their next option, search terminates. And if the agent selects an intermediate node, then the set of nodes that have been searched is updated to include the node that just got searched. And note, because of this setup, lambda can only be accessed if all of the nodes leading to it have been accessed. There's no jumping down this tree. Now, to do payoffs, I'm going to use indicators. And the reasoning is because this is going to parallel the proof that this process that we're about to define is going to be optimal. But for now, it's just to say an indicator is 1 if a node is accessed, 0 if it isn't. So for terminal nodes, it's 1 if it's selected. Since only one terminal node is selected, the sum of all those indicators is 1. Because you have to search the parent to search the child, if the child node is accessed, so is the parent. So these are the conditions that are imposed. And the payoff is just going to be the sum over all of these values with the indicator. So basically the value you select minus the search costs you incur, if you play through what these indicators mean. The consumer is risk neutral and aims to maximize expected payoffs, given the information available to them at each point in the search process.
Can you repeat what or explain what search terminates means? That means that your
when you select an option, search is over, right? So you don't get to continue your search process. This is what you would have in an OSM. When you select an option, you've selected an option.
Oh, so it doesn't mean that, I see. So I thought that if you were to open the last epsilon, you also have to select it. No.
Yes, that's actually a very good question. No, it's just saying that once you've selected something, formally the process has ended. Perfect. Good. So now I'm going to have some formulas on this slide. I'm going to explain them. This is one of the key tensions with what I'm presenting today. It's going to make sense in a few slides with examples, is my hope. So the score of each terminal node is just going to be the value. We want to score this tree, and for terminal nodes, we assign the value to the score to be the value. For higher up nodes, if all of the nodes in the subtree have already been scored, we're going to define the local value for lambda to be this formula here, which is the max over all downstream options, looking at the minimum of the scores from that option back to the node that we're currently paying attention to. And that does not include the node itself because we haven't defined that score yet. This is going to proxy, and it's going to behave just like a value inside of a box. This is, and it should not be obvious yet, but this will exactly correctly summarize the value of being able to access that subtree. And so this is how we're going to use a regular scoring formula, is by defining these v-hats. But once again, that shouldn't be obvious, maybe plausible, but certainly not obvious at this point. The other part is the script g lambda, which in our paper is much more rich in what information you can have. Right now, this script set is just the set of all things that would be observed by the point where you're deciding whether to search lambda. And the key to how we set up this model is what you learn is only learned on the most direct path to lambda. So as you wander, if you go to other nodes, you don't get additional information. So there is an exact set of information that this consumer will have when they're deciding whether to access lambda. This is that idea, which is until I've accessed Amazon, once I've searched Google, I'm not going to find stuff if I wander to other nodes before accessing this. And that's going to be key to those myopic scores. Now, the key, though, is that once you do all of this, we're going to define scores exactly the same way we always do, which is basically the score is going to take what instead of being a value is now the local value minus the score. We're looking at that expected improvement versus the cost that you pay to search lambda, conditional on the information you have when you decide if you want to open lambda. We're going to set that equal to 0. By the way, this is the underlying math used in something like Choi, which has pre-value heterogeneity that's observed. You would condition on that when you're thinking about the score because it's observed prior to search. Similar with the search cost if it's heterogeneous. Now, you might be worried this is hard to do. We can't do this. The key is that because it's a tree, you can always recursively do these things, right? You can work from the bottom up. And to formalize that, you can go to the deepest depth of the tree. Those are all terminal nodes. So you can score them using the fact that the score is just the value. When you've done that depth, you can go one up. When you've done that, you can go one up, and you just march up to the root. And that's also how...
I'm a bit confused, sorry, Dan. Sometimes you say, oh, we can do these things, but so far as I can see, these are all definitions, right? You haven't shown us anything yet, how useful that is.
Absolutely. We don't know it's optimal yet, and we don't know what it's going to... I haven't even defined how the consumer searches using scores yet. I'm just saying we can define values.
Sure.
Yeah.
We find all kinds of things, but yeah. Okay.
Yeah. But right now, this is purely just some mathematical formulas that I'm giving you intuition for, and the intuition we will find out to be correct. But yeah, yes. I'm doing the optimal scores in case, to do these first, and then I'm going to provide the intuition. We're actually back and forth on this ordering. So the key then is that the score search process is going to be that at each step, there's a set of nodes that this consumer can access. Each of those nodes has a score, and the consumer just selects the node with the highest score. So at each step that the consumer has a choice, they take the highest scored node.
Yeah, quick question. So it doesn't depend whether this optimality holds both for hidden prices and known prices, right? Or no?
For right now, think prices are observed at the root.
Just prices are observed. Okay, that's what I thought.
Although in theory, you could adjust it, and we will. But yeah, right now.
Okay, but you would have to adjust it. Yes.
Yeah. Mm-hmm. And then the key theorem, which once again we're going to wait to prove it, and even when we prove it, it's going to be mostly the sketch of the proof, is that with these scores, the score search process is optimal and generates an expected payoff of the local value of the root, which is going to be the max over all of these options, taking the minimum of the scores from that option back to the root. But before this is going to make sense, we're going to characterize demands, and then you're going to see where these formulas are arising from. And then we're going to show that this is optimal. So the first thing is actually just, we want to compare two options. We want to figure out when the properties, or more I should say the scores associated with one option, are sufficient to prevent another option from being selected. So if you knew that the minimum of the scores on the path to I not shared with J is higher than the minimum of the scores on the path to J but not I, that means there is some score on the path to J that is below all the scores on the path to I. And so I would be searched and selected in this process before J would ever be selected. I don't know that I is selected, but I know for sure J is not. So if an option is if an option is preempted, it is not selected. Now, where am I going with this? We're going to use pictures. We can compare 2 and 4. So if you compare 2 to 4 in this picture, they share the node A, so we don't care about the score for A. We care about the score for 2 and B, and I've left the bar off of 2 because it's just a value. So we compared the score for 2 and B to the value for 4. If the score for 2 and B is above 4, then if you have searched A, you can access 4 and B. So if that score, the minimum of the score for B and 2 is higher, you will search B and select 2 before selecting 4. If you reverse it, I don't know whether B is what stops this. I don't know whether 2 is what stops this, but 4 would be selected prior to 2. You can do the same thing comparing 2 to 6 and 4 to 6. The key, though, and this is where these complementarities are going to come from, is that when you compare 4 to 6, you're going to use V bar A. When you compare 2 to 6, you're going to use V bar A because they both share A. And this shared common node is why you can have drafting effects. Plain and simple, because something good happening to 2 might also be good for 4. So to formalize this, suppose 4 increases in value. I'm being vague about what that means. And as a result, the score increases, right? So 2 becomes better, searching towards B becomes better, searching A becomes better in terms of expected improvement. 2 may now preempt 6, and that could mean now that 2 is selected where 2 was not selected prior. So these changes, something good for 2 might also be good for 4. And that's the key. Now, the next thing is that local value, which kind of came out of nowhere. And I've highlighted C, but C is actually not part of this. C is part of the V star below it. The local value, though, is just the max over 5, the min of the score for 6 and D, and the min of the score for 7 and D. We're just taking these downstream values from C and basically figuring out which of them is the best candidate for preempting options that aren't downstream from C. So we're keeping track of the best option in this subtree. Somewhat similar to how we use like subgame perfection when we solve backwards. The key then is that once we have the local value and we have the score, we can define the replacement value to be the min of these two. Now, why I call it the replacement value will make sense in exactly 2 slides. The first thing is that we can compare 2 to 6 or 5, 6, and 7 jointly by comparing the minimum of 2, B, and A. I'm not saying scores, just to simplify this, the score for 2, B, and A, to the local value for C. And if the min for 2 is above the local value for C, it's going to preempt 5, 6, and 7 jointly, because we took the best of them and showed that that one's preempted. If you reverse it, you know that at least some option downstream from C is going to prevent 2 from being selected. Now, if there's no shared nodes, you can then basically do this where you compare 1 to V star A and V star C and just get a regular demand formula like what we're used to. Because there's no shared paths, you can simplify this down to a single inequality. And so in this world, this would behave a lot closer to discrete choice models. There's no drafting effects for 1 relative to other options. Moreover, you can actually rewrite this, ignore the fact that there's a downstream tree, and just think about those as the value for some option immediately attached to the root. And this is going to be the logic behind pruning, which is basically how we're going to prove that our process is optimal. So there's a lot of nice properties, but it's really coming down to the fact that this is a tree. And we're using kind of classic ways of making these trees kind of be prunable in how we think about them, working from the bottom up. I'm going to put up some formulas. This is just to show that 1, they exist, 2, they're somewhat nice, but 3, they're not that nice. And the idea is that the demand for I is going to be the probability that I preempts J for all J. But because there are different possible paths, I cannot summarize this as some value, some combination of this, the scores for I relative to the next best option. There's no next best option logic here, right? Because of the possibility of shared paths. You compare different sets of scores depending on which options you're comparing to. The idea, though, is because something must be selected, we include the outside option in this set. Because something must be selected, if I prevents by preempting all other options from being selected, I will be selected. Search volumes, or the probability of being searched, are going to behave similarly. We didn't define preempting between intermediate and terminal nodes, but it works the same way because scores are just the rule that you follow. And so you just compare whether lambda preempts all options that aren't downstream from lambda, which means prior to selecting any of those options, you would search lambda. So this is an eventual selection in the first one, eventual search in the second one. And then the bottom part is that if you want to think about the overall demand for a subtree, you can then aggregate them and you basically replace a score with a local value and it behaves nicely. So there's a lot of similarity in these formulas. And to simplify notation, I sub lambda is the intersection between the set of all downstream nodes and options. So it's the set of downstream options. Now, recall that earlier, the payoffs were of this form, right? So this was the sum over these indicators, where on the one part of this is the value you select with an indicator for whether you select it. And then on the other side is search cost that you pay with an indicator 1 if you pay them. Now we're now going to think about aggregating these. So thinking about this downstream set, we're going to make B lambda be the indicator for whether something downstream from lambda is selected. So note A lambda is whether or not lambda is searched. B lambda is whether or not something in the subtree is selected when search terminates. For intermediate nodes, trivially, BI is just AI. And we already defined VI to equal V bar. It will also be V star by that definition. So we can immediately do this for all terminal nodes. We can immediately just rewrite the formula, replacing B's and A's and V stars with V's for options. Now, in order to be able to show that this is optimal, to do all these things, we're basically going to take the proof in Armstrong, which relates to other proofs in other papers before it, and use it iteratively. So this is going to take that proof and just repeat it up the tree. And what we're going to do is we want to find two properties. The first one is inequality, that the expectation of the sum of the indicator for whether a downstream option is selected times that replacement value, the sum of across all the children for some node of those values, minus the search cost for the parent. And we want to know whether that expectation is bounded above by the expectation where you just take the indicator for whether a downstream option is selected from lambda times the replacement value for lambda. Now, if this was a box, this is just the min reformulation. The value inside of the box is a single value, so you don't have a sum there because there's just one thing inside the box. You then have a score, and then when you go up a level, you just have to show that that's bounded above by the minimum with an indicator for whether it's selected. This is how the min reformulation works mathematically. Well, it's how you can prove optimality using that reformulation. The key, though, is that for the process that we have defined, this will hold with equality. So basically, we're showing a way of pruning something. If all the children have already been pruned, how you pruned the parent. So we're now taking these indicators and we're moving them up the tree. And this is just saying that as we prune, we preserve payoffs with the optimal search process, and we only increase if it's not that process. And so this is going to be proving that the process we've defined provides upper bounds for payoffs. So it must be optimal. But I'm going to punt the formal proof of this to the appendix. This slide is just arguing that we can prune. This is this idea that you start at depth D, maximum depth, and we've already pruned there because AI equals BI and VI equals V star. And then if you have pruned up to depth D+1, you can apply this lemma to all nodes of depth D, grouping them properly and moving now to one lower depth. So each time you basically apply lemma 5 to all options of depth D, and then D-1, and then D-2, and then D-3, onward and upward until you get back to the root. So the meat is really in lemma 5. Or, well, I think it's lemma 5 in the paper. The meat is this lemma, though. Once you have that, you can prune. And the key is that continuing this process, you're going to eventually get back to B lambda 0, V hat lambda 0. The score for the root, think of it as infinity. So the local value is the replacement value. And that's just that V hat lambda, which I write out in the theorem. It's that same formula, though. Since the upper bound is achieved, the score search process with the scores how we assign them is optimal. So this is the idea that basically we define these scores. There's obviously a lot more math underlying these arguments, but the idea is that how you prove it is you show that it's optimal in each of the subtrees. You start at the lowest subtree. Basically, we're showing it's optimal of all subtrees of depth D, then D-1, and really we're proving like a local version of optimality that we then bring back.
Dan, coming back perhaps to Heskey's initial question. So, are you going to show us why this is useful? I mean, how this could be applied to anything, in practice, how to operationalize this and so on?
Yes, though, as I kind of guessed, I'm going to have the time to discuss it, not the time to go through it. Yes, I will, but briefly is the answer. We have answers to this, but for the sake of time, I wanted to spend a bit more time on the model itself. But we're now actually going to talk about just kind of a direct and clean application. So in this world, because we've set up now this optimal scoring rule, if we think about passive belief consumers that hold the belief up to a point and then update their belief by observing the true price, basically the consumer is going to optimally score given their belief. So if they're wrong, then they'll have incorrect scores. And this is how we almost always do ordered search with some sort of observation of prices. So the consumer starts her journey. One of the things she's learning is prices. She believes, though, with 100% probability that the vector of prices she faces is P hat. Pi hat then is the price that she anticipates for I. The consumer discovers the true price of I after searching a specific node. This node could be common knowledge. It doesn't necessarily need to be for some of our results, but for now, think it's common knowledge. And the consumer has passive beliefs. So if you observe a deviation for one, you don't believe it affects, you don't update your beliefs about anything else. So if you observe...
So what you're showing here, is this now something that you're going to assume, so I guess if I believe that in equilibrium, say, prices are, there's some randomization or whatever, that I can't think of this. So
you can, but not in this simple example. There's
so
absolutely
supposed to be now an example, or what? I'm a little bit lost. Prices. Is this now an example of what you're going to?
So think of this as, I want to illustrate how the properties of selections are affected by prices. And what we want to think about right now is just when the price is discovered is going to be important for what effects we get. And actually, the next slide is going to be saying if prices are advertised, we can basically come up with a decomposition of the parts that this price is going to have a positive effect on nearby options and a negative effect. So we're going to come up with a decomposition of demand changes if a price of a nearby product changes. Overall, though, depending on when a price is discovered, is going to have a lot of relevance for whether products could be cross substitutes. But
9 minutes then.
Yep. Oh, 5. You said 5?
Nine.
9. Okay, good,
Yeah.
good. Yeah. So you're exactly right. Right now, though, we're setting up a model that, to the best of my knowledge, hasn't been solved before on the demand side. A lot of the meat of this paper, as we're presenting it today, is the demand side. In the paper is some equilibrium analysis, but it's generally in special cases rather than the overall model, right? We're very limited in the models that solve hidden prices in ordered search models that have a single box to open and options inside of those. Many boxes, I should say, but a single option in each box. We can extend those by a bit, but overall right now, we just want to think about the structure of demand and how the price for I is going to affect the demand for J. Now, of course, there's arguments here. So if you have complementarities, I can set up a formal model in which mergers are good in equilibrium, right? But I'm not doing that here. So the key, though, is that the consumer is going to have these beliefs. By the way, for this part of it, it could be a distribution over nodes where they discover it. But what I'm using this to do is actually to motivate an effect that I'm going to have in the following slide. And I'm going to set the timing of discovery to a very specific node to quantify the effect of an advertised price change. And so what I'm going to do is I'm going to consider two options, I and J. I want to think about how the demand for J adjusts with the price of I if the price is advertised prior to search. So there's an adjustment on PI, the consumer observes it. Now we're going to think about a hypothetical world, though, where they don't. And we're going to say that in this hypothetical world, they exactly observe it at the common ancestor. And the reason we're doing this is we want to isolate the changes in the shared scores from the changes in the non-shared scores and how those then propagate through to demand changes for J. So in the world where this price is discovered exactly at that point, DJ is increasing in PI and decreasing in PI hat. We're shifting the shared nodes with PI hat and the non-shared nodes with PI in this setup. So when we want to think about the advertised demand, you set the two prices equal and then take the derivative. Right, so you set the prices equal before taking the derivative. But that's overall going to just equal the derivative of DJ with respect to this hidden price I, evaluated at correct anticipation, plus the derivative of DJ with respect to the anticipated price, evaluated at correct anticipation. So the blue part is going to be the local competition effect, and the magenta part is going to be the drafting effect. And the idea is that they will always go in opposite directions, and which one dominates is not clear. We can set up a model with a single box and give you conditions in that world to give you kind of an idea of why these might be complements or substitutes. Another way to say this, when drafting effects will dominate local competition effects. But the idea is that you can do this decomposition. And even if a price was buried, you could still do this decomposition by using that common ancestor to still break the parts. You just wouldn't go all the way back to the root. Now, of course, if the price is discovered at
then, I mean, just maybe coming back to, again, you know, what is this, what we learn at, you know, Sandro's question earlier about these drafting effects and local competition effects are known, right? I mean, we know this from shopping malls, say, right? Or whatever, you know, supermarkets, if the price of one thing at one mall declines, that has two opposing effects. And you can exactly in any stand, you know, it's well understood that you could sort of exactly decompose it. So what is it that you think now add to, you know, we already know that these two opposing effects, and we can decompose the overall effect into these two.
So we can.
How many people go to the mall, right? That's the drafting effect. How is, you know, that's the complementarity. And then once among the people who go to the mall, then we're going to have what you call the local competition effect, the substitutability.
So correct me if I'm wrong, though. You couldn't have very close products be complements, semi-close products be substitutes, somewhat farther away products be complements, and then somewhat farther products.
I guess what you're showing now here, it doesn't show that. I mean, what I'm saying.
No, I'm just saying this is just to like this is a model that, to the best of my knowledge, has never been solved before in setup. So like with 50 minutes, I'm going to focus on that. But I can set up a tree where basically, if you set up the tree, I can make anything complements and substitutes except for things that don't share paths, by basically thinking about adding correlations in the right way. I'm not showing that here, but the idea is that even things that are very close substitutes in value can have drafting effects that dominate. And more importantly in this setup then is when we think about something like nested logits in a richer environment, we're well beyond that mall model, right? If I really want to take that mall model and have in that mall, there are floors. In those floors, there are wings. In those wings, there are stores. In those stores, there are aisles. In those aisles, there are heights, right? Like, if you really want something that kind of can be more refined like this, where you might have that two things in the same aisle are complements, two things farther away in the same store are substitutes, but dresses in one store are complements with dresses in another store, or something wild like this, you could set up a model. My goal is...
Can you elaborate on this thing that you can have correlation, which is quite strong, but you still have complementarity? Because if I understood correctly, the way you model things, your final value is the sum of values on the way?
Yes, but we can actually...
So, I mean, you are correlating one of the epsilons, but...
Well, technically, anything that...
The other ones...
So if you think about two cars at the same dealership, you could learn about correlations when you search... same dealership, same brand. You could learn about correlations at the brand level, the dealership level.
No, that's fine. What I'm trying to understand is you are saying you can generate the drafting effect dominates the local competition effect, even if these epsilons are highly correlated. I would suspect that's because the total epsilon is not that correlated.
Because it's actually, I mean, you can do it just by using search costs, just by making a consumer closer to one of these than another. So actually, the way I would most easily do it is by really extreme example here, just to make it clean for this argument. You can basically have it so pathways get shut off on you. So like when you can access one, the other one's shut away from you. So if you're not sure 50-50 which thing's going to be inside of a box or something like this, but more think up a level, you don't know which of the two brands is carried, but you know one of the two brands is carried. If you think one of the brands is better, but you don't know which one's there, it's going to help the other brand. Because on the day that you're not the brand that's there, the other brand still gets the foot traffic. This is the most extreme.
But how correlated would these brands be? Kind of your...
Well, they can be extremely correlated in
value.
They're
not. I mean, if they're not available at the same time,
exactly.
So they're negatively correlated.
Coke and Pepsi are very correlated, but at restaurants they only have one of them.
Most people
don't know which restaurant they're gonna, which of the two is gonna be at.
Right, but of course that kills local competition because they never compete. So it's kind of
I said I'm giving the most extreme example that is the most stylized way to show it without having to like explain more math. Right, I'm giving by far the strongest example.
Yeah, I understand that, but it just
some people have Amazon as their homepage. Some people have Walmart as their home, right? Like some people happen to get a search where one's higher. Some people happen to get a search where the other one's higher, right? There's a lot of ways you can relax this and tell similar stories. So
I guess kind of agreeing with Volker, would be nice to have, let's say, less extreme example where we see this.
So I agree, but I don't think I would be able to do it in an appropriate amount of time to.
Well, no, but I mean, eventually, or
it's in the paper. I mean,
it's already in the paper.
I mean, to some extent, it's in the paper. We plan to add more, though.
Okay.
So the idea, though, is at the highest level, we're just aiming to generalize Weitzman, right? We're aiming to be able to do this search model so that you could, for example, have search among platforms, within platforms, so on and so forth. So you could take a mall model and think about different areas of that mall. The idea is that we characterize key features of this search process and explore the role of price discovery. One thing we don't do today, but you don't actually need to know the exact structure of the tree. So for example, if there are categories at Amazon, you don't necessarily have to know those categories up front before you start search. And the other part of this is that we analyze specific versions that I don't cover today due to the sake of time, which I think I'm going to be ending exactly at the minute mark. But the idea is one thing you can do is you can show that even very, very rich trees, you can motivate nested logit with this tree, which isn't that surprising, but this is a costless recall setting versus the normal way to motivate logit is with an infinitely costly recall setting. You can do onions where there's no shared path. And there we have equilibrium properties. We can solve those models, characterize them. And then there's a one box example. And that's basically just showing all this intuition in the mall setting. The goal of this paper, though, is to take intuition that you might have from hoteling or mall models and to interact them with ordered search in a meaningful way. To get the richness of an ordered search model where you have many products and different things you can search, but then to interact it with versions of closeness, proximity. And what we don't want, though, is just close or not close. We want some gradient of closeness, right? And that would be things at the same dealership are closer than things at different dealerships. Cars in the same brand are closer than cars in different brands. Okay, I'm going to end here and then open it up for questions. Thank you all for listening.
Then I don't know. I mean, maybe it's just me, but it would be nice to see some sort of example that shows usefulness of how to operationalize, what is it that we have now, you sort of always say, oh, we can do these things. It's very general, but okay, so what? I mean, you can write down something complicated and sort of represent it somehow, but then what?
Well, so
Hesky is, maybe an empirical application. For instance, I don't know, it doesn't have to be empirical, but somehow, this is now cool. Yeah, maybe empirical. Yeah, so I guess.
Empirically, actually, so one of the key things is there is kind of an invertibility version of this that we're not talking about, but that if you see actions, you can infer something about these underlying distributions. That's not something we're talking about. We're trying to decide if it's going to be in this paper or a different one. But there is a way of going backwards, right? The first part, though, in my opinion, whenever you have a new model, you have to understand the demand side before you can understand the supply side or how to estimate it, right? Like the first order problem here is solving a model that took a long time to solve. like I know that's kind of a terse answer, but it's kind of like we understood nested logit theoretically before we really started using it in estimation or something like that, right? Like you have to kind of parse the model first. Now, however, saying that, I think there is an inherent empirical application because we are allowing for a system that admits complementarities. And so my guess is there's probably some way of setting up a tree that would be easier to estimate, especially if you observe the structure of search. So if you saw, for example, how many searches were at Amazon, how many were in the category laptop at Amazon, how many searches were at Google, and you had cookies on somebody's history, you might be able to then infer things in this model. To the best of my knowledge, there's no other search model that could be used there, right? Like I don't know of another search model that could allow for a consumer journey that would be, I wander towards Amazon, I don't find what I like, I go to Walmart, I wander around in Walmart, I then go back to Amazon, right? Like, and so part of this is the first stage is to get the model. We do have some equilibrium analysis in the paper. Some of it got pulled because we have to edit those sections. But the next stage would be, in my opinion, an empirical application. Here, it's just pointing out that we're essentially getting old style intuition inside of an ordered search model.
I mean, that in itself can't be the answer, because, if it's just to get some, ordered search model where you get these, I could write down a simpler model, right, in order to get the old style intuition. So I guess it's somehow you write down quite a complicated model, and then sort of, I guess it's supposed to capture something, and it must be operationalizable somehow. I must be able to do something with this, right? I mean,
so I'll give you the example. Simon's got another paper where you're deciding whether or not you want to search the platform, right? There's a monopolist platform and you're deciding whether or not you want to search it. And the platform they consider is Amazon. The thing is, though, we know that Amazon has an in-house search engine, and they have that in-house search engine for a reason, because people don't just appear at Amazon and see everything at Amazon, right? Like, while there are existing ways of taking an ordered search model, by far the simplest is you take an ordered search model and you put things inside of boxes, right? So now boxes are going to have multiple things inside of them. You now have basically binary closeness. Things are either together or they're apart. There is no other version of that world. Gradients of closeness, in my opinion, are super important, right? Like, because like there's all these stories that we see in the real world, which are really hard to justify in a regular ordered search setting. So like advertising for Palm, and why other companies basically put their products in a similar part of a grocery store and advertised that pomegranate was in there, was because Palm advertised the health effects and people started looking for pomegranate juice. And then all these other companies cash in. Or the example where one company that's telecom advertises a sale and people end up switching from that telecom company to another. And in that setting, it's probably because they were all brought attention to this market. And so if you think about it, there's search once you appear, but there's also that decision to start search versus an outside option. And so if you think about it that way, there's a drafting effect on the call to attention. Now, I'm not saying these stories are necessarily new, but to the best of my knowledge, there wasn't a model that could just cleanly get you a way of writing them down in a way that, isn't kind of rigged to just get that individual property.
Can I change topic?
Yeah.
Right. So I was just wondering about the novelty of the class of demand system that you're obtaining here. Just going back to Choi Dai Kim, for example, right? So what they showed us is, if you do ordered search, you're getting a demand system, and surprisingly, that demand system can also be derived from discrete, classic discrete choice, right? So I'm thinking, in your case, so what if you had some version of multi-stage discrete choice with what you call, infinitely costly recall, right?
You can absolutely get it in those settings as well.
Yes. So my question is whether you get the Choi Dai Kim version of the equivalence results between, the type of search models you showed us and that multi-stage discrete choice.
This is actually a really good question. It's one we have started to think of, but don't have a great answer to. I can give you the answer, though, of I can approximate infinite search costs in this world.
Infinite recall cost?
Infinite recall.
Yeah. Okay.
And basically, the way you do it is by raising the value of the prize and deforming the search costs in a way that preserves the scores.
Yeah.
And basically, what you make it is so that when you open this box, it's so good, but the cost is so high that by the point you make the decision to open the box, you're just going to select what's in it.
Yeah.
So it's worth saying that I'm not sure if they're fully nested, but they're certainly one can approximate the other. I'm not sure that's the perfect answer. But the other part of this is, like, for example, the onion model, which we don't show today, but I put here just in case it was relevant, is this idea that you can add different steps towards the same option. That then has the same CDK style reformulation, or Armstrong, whoever you want to attribute that reformulation to. And you can make it as many layers as you want, and basically you just get a bunch of scores and a min up the line.
Right.
And interestingly enough, this reformulates with advertised prices to a DCM, but of course, Choi Dae Kim's would not reformulate to a DCM with hidden prices, or at least it would only in equilibrium. But this actually reformulates to an OSM, a regular OSM. Another way to say this is wherever this price is buried, you basically treat the scores up to that point as one layer, and the value under that point is a different layer. So there is some intuition here gained in these sub-examples, right? That you can have this much richer search process without shared paths, and you will get basically hidden price games back. So adding steps to a game does not make it any harder. And actually, I can show using the same trick I did in the first paper with Simon and Maxim, which is that you can construct these to match any discrete choice model. I can construct one of any depth to match any discrete choice.
Yeah, I see.
So it's all completely, in some sense, scalable. Shared paths, though, especially branches that branch, that branch, that branch, is a much harder problem to consider.
All right, thanks.
Yeah. You don't even have to know if you're going to like successfully open the box. You can have a probability of failure in opening the box and it would still work. Yeah. So this model is very generalizable. And I understand that also leads to the very correct argument that we're not going for a specific point here. But it is a fairly flexible setup. The original way I thought about it is to model platforms, the incentives of those platforms, but allowing for search within the platform. And this was originally where this demand system came from. But then it became clear that it basically kept scaling as many times as you wanted. And so this paper with Simon and Maxim is about doing that, just setting up the demand systems. Okay. Any other questions before I cut the recording? Okay, I'm going to stop the recording here.